All right, hello AP Statistics. This is sample means section 7.3. You'll need your normal distribution table. You'll need a graphing calculator. And once you got those things, paper and pencil, we're ready to go. All right, so here's what I have. I have 386 pennies that I collected from a bank all in one sitting. And since those are the pennies that I own, I'm going to call that my population. Okay, and I'm going to identify that with a capital N. And what I can share with you is a couple things. First, if you found the average year for all those pennies, it would be 2006.6 with a standard deviation of 8.018. Okay. Further, if I were to make a distribution of all of those pennies based off year and put it into a graph, you would see the graph that we have below. Notice that it is labeled year of pennies, okay, and it's from 2006, from 2000. Okay, so if you read 2000 and look at the year 0, that's what is represented here. Okay, so years since 2000, 2000 begins here, and you can see, I think here I have 16. Okay, all right, so here's what I asked first. Same type of question that we've had all semester long. Look at the graph and describe the distribution of the population of pennies based off of year. Okay, now you can see that it goes back as -11, as far as -11. And when you think about number of years since 2000, -11 is really the year 1989. And 2016 would represent the 16 here. And you can see that there's much more representation for the earlier years than there are for later years. That would seem to make sense because as time goes on, the circulation of older pennies tend to fade away. Okay, so if I'm asked to describe the distribution, here's what I would share. I would say the distribution of pennies based off year does not look approximately normal. It looks actually very skewed. Appears skewed toward lower years. Okay, or you can say skewed left. Okay, and that is the first representation for describing a distribution. Okay, we talk about shape. All right, second thing is outliers. And I will tell you that if you do an outlier test, okay, doing 1.5 times Q3 minus Q1, okay, you'll find that Q3 is the year 2014, and Q1 is 2000. And if you do all that math, you get 21. And since there are no numbers for years that are bigger than Q3 plus 21, which is 2035, and none smaller than 2000 minus 21, which is 1979, I believe. I did that math. Yeah, there are no outliers. Okay, so the lowest we have is 1989. That is well within the lower fence, and 2016 is well within the upper fence. Okay, so there are no outliers. Okay, further, okay, if I were to keep going, the center. Okay, so center is the halfway spot, and the halfway spots of this divided by 2 is 193. And so here's the idea. If you want to count inwards, okay, to 193, meaning like this is 42, this is 33, and so on. Keep going. There's 9 here, there's 9 here. Add up all of these until you keep getting into a column that has the 193 in it. You finally get to it on each side, going from left to right and right to left, under the year 2008. Okay, so the center is 2008. Okay, and then I have a spread, which we've already talked about, the lowest value to the highest, of, we'll say 1989, okay, to 2016. Okay, and so that's how we'll describe our distribution. Some may want a little bit more information about how I found the 2014 and 2000 with respect to Q3 and Q1. You could put all of these by counts, okay, in your graphing calculator, create a list of 386 numbers in your L1, and then do a 1-var stats, okay? Or if you take 386, okay, found the median, okay, and then cut each of those lower halves and upper halves in half again, respectively, you would find that this is your lower bound, lower quartile, sorry, 2000, and then your upper quartile of Q3 is 2014. Okay, so that's how I did it. I did it ahead of time so we wouldn't have to spend time counting all that out. But in the end, there are no outliers. Okay, now here's what I had students do. This is actually my bag of pennies. This is my big N population, 386 pennies. And what I typically did was have students come to my bag. They would pick out 5 pennies, look at all 5 pennies as a group, and write down the respective years. Okay, and imagine I did that. I've got 2003, I did it again, I got 2008, I got 2007, and then 2006. And another 2006. Okay, I put the pennies back, I shake them up, and I let my next student do it. Okay, and I keep repeating it until every student in the class obtains 5 unique pennies, okay, and then writes down the respective years for each. Okay. Now, once I did that, okay, once you write down the years, okay, you place the pennies back in the bag, I'm going to find the average year for those 5 pennies, okay? And since my N was just a little N equals 5, my X bar, if you were to add these all up, okay, and then divide by 5, you would find that for this group, this particular X bar, you would get 2006, okay? Now, the students in the class all had 5 different sets of numbers based off the pennies that they chose, and they had a different X bar, okay? If you think about all the little X bars that could be created, okay, being 386 pennies and choosing a group of 5, we have 68 billion different ways, okay? However, I don't have that many students, okay? And just because I had that many, if I did have that many students, it doesn't mean we'd all pick unique sets of 5. But if you were to pick every single possible group of 5 from that set, okay, that population of 386, this is how many you would have. And if you were to average all those independently amongst groups of 5s, you would have a complete sampling distribution, okay? For us and all my students, we have 82, okay, in our sampling distribution. And it's far from 68 billion. Nevertheless, it still provided us some good results, okay? So here's what I'm gonna do. I'm gonna keep this 2006 in mind, okay? In this special year, if you're looking at this and saying, I can't pick all these pennies, okay, your pennies are different from my pennies. And further, even if you had these sets, you're like, I don't want students grabbing pennies with COVID right now. Here's what I did. I've attached to my note sheets a table that has every single penny based off year included, and they are numbered from, as you look up here, top left-hand corner, from 001 to 386, and they're numbered from lowest to highest. Okay, so I told you earlier I had 16 pennies that are from the year 2000. If you look in a row here starting with 2000, I guarantee you there's 16 of them in there. Okay, and every year is represented accordingly in this table as you saw in your distribution table. Okay, so for my students, what I said, instead of coming up to my class in the front and picking 5 physically, what I'd like you to do is use your TI-84. Okay, and then we're going to do random integer. And the smallest penny is identified with the number 001. The highest is 386. And I want you to pick 5 unique ones. Okay, and once you got your 5 numbers, okay, first you had to make sure they were all different. Okay, so make sure that when your calculator gave you 5 numbers that they were different. If one repeated, I asked people to hit enter again, and the next number would replace one of the numbers that repeated. Okay, so you'd have 5 different ones as I had students pull from the bag. I didn't have students pull from a bag, look at a number, write it down, put it back, pull another one. I had them just pick 5. Okay. Okay, and then once they grabbed their 5, they corresponded with a certain year, another year, another year, another year, and then they would average those just like we did previous. Okay. So we all had our own unique X bar. If we had an X bar that was a non-whole number, okay, so it was a number that had a decimal, I asked students to round it, okay, and that says that right here, round to the nearest year, okay, and that made our graphs look a little bit more manageable in terms of coming up with some type of distribution with our 82. Okay, so keeping in mind what our X bar was, let's test the conditions for standard deviation. Okay, and we have a 10% rule. And remember for 7.2, I'm writing this kind of directly under me right here. 7.2 had this rule. It was little n is less than or equal to 1/10 your big N. And the sample size that you had was 5. And your population was 386. And that more than qualifies. Okay. Now you're like, that was 7.2's work. What about 7.3? 7.3 is the same. Okay. The rule would still be the same. Okay. Your sample size is 5. And it's 386. And so this works. Okay. So the rule that we would use for 7.2 applies for 7.3. It does not change. And what you would say as your standard deviation is valid. Okay, now, here's where things are a little different, okay? For normality, okay, remember that we use n times p is greater than or equal to 10, and n times 1 minus p is also bigger than 10. Okay, and if you try to input values into this for 7.2 type work, which related to proportions, it worked fine because you had proportions in your problems, okay? Here, we don't have proportions. We have, and I'm circling this really big in your title, we have means, okay? Which means you have a completely different criteria for your normality, okay? So here's the deal. If your N is less than 30, okay, you're gonna have to take all your little samples of X bar and you're gonna have to graph them. Okay, and once you graph them, you have to make sure that there is no skewedness. Okay, if there's skewedness in your graph, then it fails. Okay, if there's not skewedness, then you are clear and you can say that your sampling distribution should be approximately normal. Okay, now, while the next part doesn't follow our current criteria, you will like it. If it's not less than 30, then it means it would have to be greater than or equal to 30. Okay, and if your sample size is ever 30 or more, then we get to follow something called the central limit theorem. Okay, and what this means is that your distribution will be approximately normal. Okay, and again, we'll say it by the central limit theorem. Now, you'll notice that this is in all caps. You don't have to write out the whole phrase, okay, or the whole title. You can just write CLT. Okay, and that saves us a little bit of time from having to do a little dot plot. Okay, so what do I mean by that? Well, because our samples were of size 5, and I did have 82 of them, they needed to be graphed. Okay, so here's what I did. I made a table that looks, a chart that looks similar as to before. The only difference is I labeled this on the bottom a little bit differently along the horizontal axis. Instead of saying year of pennies, I said the average year. Okay, so this is all the little X bars that we obtained as a class. And again, they are of samples of size 5, and there should be about 82 of them. Okay, so my X bar was 2006. And so what I did is I put this graph on our whiteboard, and I went to 2006 and I filled in my square. Just put a little dot there. Okay, and then when I was done, I had all the students do the same thing. Okay, and when all the students did that, we collectively came up with this sampling distribution. Okay, and if you look at that, you're like, well, that no longer looks skewed. Okay, is that fair to say? And you're right, it doesn't look skewed. It's no longer skewed. Okay, which means my test for normality is okay. Test for normality is good. Okay, which means my sampling distribution should be approximately normal. Okay, now keep in mind that again, there are 386 pennies in my population. If I were to choose all groups of 5 and average each of those individual groups of 5, I would get 68 billion. I'm just going to put a B there for billion. Basically, little dots that would appear. Okay, and had you done all of them, it should have a roughly, I'll just say, symmetric shape for sure, and it will be mound shaped, and we'll say approximately normal. Okay, now we couldn't do all 68 billion of them, but for my sample of 82, this isn't so bad. Okay, now I'm going to refer back to this off and on in just a second, but some things I want to identify first, just before we begin, is that amongst my 82, okay, if you plug these all in your graphing calculator for an L1 and did a 1-var stat, you would find that your Q1, okay, is 2003. Okay, you'd find that your Q3 would finish on 2008. Okay, and you'd also find that your median is 2005. Okay, so just some observations. One, your shape changed. You went from something in your population that was skewed towards lower values to a sampling distribution that looks much more symmetric. Okay, and almost, we'll say, even approximately normal. Okay, there's much more absence of skewedness here compared to the original graph that had a lot of skewedness with the population. Okay, second thing, you could do an outlier test for this, and your Q3 is 2008. Minus Q1, which is 2003, you get 5. Multiply that by 1.5. And you get 7.5. And if you add that to Q3 and subtract it from Q1, okay, you're going to get an upper and lower fence that is more than satisfying to show that we don't have outliers. This becomes 2015 and a half. This becomes 1996, 95, sorry, and a half. And I don't have any values lower than 1995 and a half or 2015 and a half. So there's no outliers. Further, okay, notice that your median 2005 is a little smaller. Okay, it was actually a little bit higher when we looked at previous work. Okay, with our population representation. Okay. Finally, the last thing is for our distribution. If you look at the spread is much smaller. Okay, we don't go from 1989 to 2016. We go from 1997 to 2014. So it did, the variability did shrink quite a bit. Okay, and that's what it asks here. It says describe the sampling distribution. Okay, and the way when we think about distribution, I answered it kind of the way that you remembered in the past. You talk about the shape, again, that it looks much more symmetric. Okay, it looks like if you put more in there, it would look approximately normal. More X bars in there, you'd probably take a more approximately normal shape. There are no outliers. Your median, your center did change. It dropped to 2005. And again, your variability, your spread was much more reduced. Okay, it went from a much wider range to a more contracted one. Okay. However, when we're talking about describing a sampling distribution, I usually want 3 different things. Okay. And the first thing that we'll look at is the shape. Okay. And what I'll say is the shape of the sampling distribution. I'll just put this "the" here. Okay. Is, I would say, you can say symmetric. I'll be a little bit more brave and say it looks like it's approximately normal. Okay, based off the 82 that we have. Okay, there's definitely no skewedness there. And then what I want to do is I want to find a mean and I want to find a standard deviation. Okay, now, when we thought about proportions, okay, from the chapter before, section before, remember that the mean, okay, of all of your p hats, okay, if you averaged every single p hat that could exist from your population proportion, was always equal to p, all right? And I'm not talking about proportions this one, I'm talking about averages. And what I can share is that the mean of my population should be equal to the mean of all my samples. Okay, when I say samples, all the little X bars that I created. Okay, and so if I look at the original data, it was 2006.6. Okay, now a little secret. Okay, if I were to average all my little X bars, I'm going to go back just 1 second. If I were to take all these values here, put them in my graphing calculator for and put them in L1 and do a 1-var stats, you would find that your X bar for this group, okay, and that's not really the population of X bar, but of at least the 82 that we did, you would find that we would get, had it, 2005.34. Okay, and so I'm going to put that right here, 2005.34. Is that the answer, since that's what happened in our set of 82? Not really, okay? Really, the answer is this, okay? And why do we trust the original mu, which is equal to the mu of X bar, rather than what we found in our 82? And it's because this right here is just for the 82, okay? Had I done all 68 billion, okay, of the X bars that could possibly exist, you would find that this, okay, would actually get closer and closer. And if you did all 68 billion of them, it would actually equal the 2006.6. Okay, so in theory, if you did every single group rather than just the 82 that we did, you should get this 2006.6. And that's what we'll write and what we'll go with. Okay, why did I do this little average of the 82s? Okay, X bars, just to show you that this is still pretty close to that. Okay, we're only a little more than 1 year away from what the true mean sampling distribution should be, but but because we only had 82, it's not going to be perfect. Okay. Similarly, I believe that when we did the standard deviation of all my p hats was p times 1 minus p all over n square rooted, okay? And this had a p hat to it. And because I don't have proportions here, I have something a little bit different, okay? And what I'm going to say is that the standard deviation of my little X bars will be equal to the standard deviation of my population divided by the square root of n, okay? Now, from before, okay, just to remind ourselves that my original standard deviation, and I may have to bounce back to find it. So excuse me just for a second. I'm going to bounce back a couple screens. Is this right here, okay, 8.018. Okay, so I'm going to put that on back on the top, 8.018. Okay, and divide it by the square root of n. In this case, it is 5. Okay, and if you do that, okay, you would get 3.586. Okay, and so that's what the standard deviation of my sampling distribution should be for all 68 billion. Okay, now again, we only did 82, and here's what's kind of cool. For my 82, okay, just our small representation, you would have found that if you put all those data values in your graphing calculator, we know this would be the mean. Okay, that would be the mean of all your X bars for our 82. If you had standard deviation for our 82 as a sample, you would get 3.63. And you can see how super close that is. okay? So our group of 82 did a pretty good job representing that true 68 billion, okay, different ways and little averages that you should get. But again, it wasn't exactly the same, as it would be really hard to do, okay? All right, now, what am I going to do with that? I'm going to help use that and that information and apply it to a z-score since my standard deviation is valid. And since I do have a rule that says that we should have an approximate normal distribution to find more information about some certain tests. So we've done 5 pennies. It says, if a random sample of 5 pennies are chosen, what is the probability of obtaining an average year? And then part A says less than 2010. Okay, so I'm going to draw my normal distribution. Right down the middle, I'm going to draw mu. And I'm going to write 2006.6 because that is my population mean. Okay. If I were to take my standard deviation and do that 8.019 divided by the square root of 5, okay, you do get 3.586, and I'll just use that as my standard deviation from here on out. Okay, and if I were to add that to this 2006.6, I would get 861 2010.86. Okay, so 2010.86. One particular year, AP wanted students to, if they had drawn a graph, to not only indicate the average for the population, but to also draw one standard deviation in either direction. Okay, and so that's what I have here. Now, what do they ask for? I'll put this in a different color, like yellow. They asked for 2010 or less. So 2010 is pretty close to what I have listed. I almost at my standard deviation. 2010 is right here. And they say less. So less means shade to the left. Okay, and what I'm going to do is I'm going to do a z-score. So z is equal to, and from the formula that you had on the previous side, it's similar to what you did back in the earlier chapters, but instead of having an x here, you have a sample of size 5. So instead of an x, you have an x bar. And my x bar was a consideration of 2010. Okay, minus the mean. Mean is 2006.6. All over the standard deviation, which is 3.586. Okay. And if you do all that math, you get 0.95. Okay. And then you can do the norm CDF if you like. Okay, some people like that. Norm CDF. I'll just write it since people are tending to use that more and more, at least in my classes. But because you're shading to the left, you have to pick a low value, a low boundary, LB, negative 1,000. An upper boundary, which I'll call 0.95 with respect to a z-score, upper boundary. And then a mean and a standard deviation, which is representative of your standard normal distribution table. So there's your mean and your standard deviation. And if you look all that up, okay, you end up with 0.829. Okay, so we have an 82.9% chance of obtaining a sample of 5 pennies where their respective average amongst those 5, based on year, is 2010 or less. Okay. All right. Similarly, this one just says greater than 2011. So again, if I graph this out, I'll try to make it look like the previous one. Here's my normal curve. Okay, I'm going to draw mu just like before. Here's one standard deviation away. 2010 point. Sorry, that should be 186. That didn't change our answer from before, but. All right, and we're interested in values that are bigger than 2011. So I'll make 2011 here. And I will shade it to the right. Okay, and then we'll do another z-score, very similar to what I had before. There's my pen. All right, so we'll do a z is equal to your x bar, which they're asking about obtaining 5 pennies that have an average year of 2011, minus the mean of your population and your sampling distribution, same thing. So 2006.6 all divided by 3.586, which is the standard deviation of your sampling distribution. And if you do this math, you get 1.23. Okay. And if you look that up on your chart, you'd have to eventually subtract from 1 if you looked it up on your normal distribution table because you're shading to the right. Or if you had done a normal norm CDF, your lower boundary here is 2011, and the z-score that corresponds with that is 1.23, and this gives you 1,000. And now we have a mean of 0 and 1 with respect to our normal distribution table. Lower bound, upper bound, mean, standard deviation. Okay. Again, you can look this on your up on your table, get your 4-digit probability, and then subtract that from 1 because this is a greater than. If you do that, you get 0.101093, okay, which is the same as what this would provide as well. Okay, so again, 7.2, just to backtrack for a second, you had z-scores also, but you had them with proportions. Okay, and you had a formula that looks like this. Okay, and now 7.3, you have a new formula. It's x bar minus the mean divided by the standard deviation over the square root of n. Okay, and that's why we follow this one for 7.3. All right, and that is about it. Okay, so again, look back at some of the older slides if you want to think about what a sampling distribution is. Most sampling distributions are super big. They have outcomes where you may have, again, as I shared with you, many billion possible answers, okay, for X bars, but we'll just do the samples that we have, and again, we can get a pretty good idea of what's going on just based off our small samples, okay, and showing that, yeah, maybe our distribution is approximately normal, and we can create some results based off questions using a normal distribution table, okay. All right, this is just a summary, okay, of everything that we've talked about. This is the mean standard deviation of sampling distribution of X. Okay, this is your title. This is the formula that we'll use for a z-score. This is new to 7.3. When you did this earlier, you didn't have X bar, you just had X's, okay, and you didn't have the square root of n. Some people will say, why don't we have the square root of n in the past? And my answer to that is you could have had it. Okay, you could have put the square root of n there. However, all the problems that we've had in the past, considering chapters earlier in the semester, had sample sizes of n equals 1. Okay, and what we would say is, what is the probability, for example, of obtaining 1 penny that is less than 2010 or greater than 2011? Okay, and we only deal with single samples of size 1. As to now, where we're dealing with grabbing a group of items, averaging them together, and saying collectively, what is the probability that that group is less than, for example, 2010 or greater than 2011? Okay, we talked about this earlier. The mean of the sampling distribution is equal to the population, provided that you use every single sample average within that of a certain sample size. Okay, 10% rule uses this formula, which is what we've done in the past, and it applies to this new standard deviation, which is your population standard deviation just divided by the square root of n. Remember that the mean of sampling distribution is equal to the mean of the population. That is no different from what I just wrote here. It's just written in words. And then finally, if your population distribution is skewed, okay, and as long as your sample size is greater than or equal to 30, then your sampling distribution will be normal by the central limit theorem, okay? So here's what it's saying. Again, if your population is skewed, I'm going to draw this on the bottom, okay, and your n is greater than or equal to 30, okay, then you know that your sampling distribution will be approximately normal. Okay, if n is less than 30, then you don't know, okay? And then you'll have to do a graph like we did as a class. We graphed all our little X bars, okay? And we found that from our work that it was okay. All right. Something also to keep in mind is this. This is only needed if your population distribution is skewed. If your population distribution, sometimes we don't think about this, is normal, okay, or approximately normal, okay, it means that it doesn't matter if your n is bigger than 30 or less than 30, okay, these are going to be normal too, okay, and those aren't great drawings, but they're both going to be approximately normal. So this central limit graph, central limit theorem is really only important when your population distribution is skewed or they don't tell you what it is, okay? If the population is supposed to be normal to begin with, as you see right here, if it's normal to begin with, this is highlighted in yellow, normal to begin with, then your samples, regardless of size, will be approximately normal as well, okay? All right, very good. Here is the assignments. Okay, you can see that there are 3 questions here, 4, 5, 6, 7, 8, 9. 9 problems to finish off this chapter 7. If you have any questions, you holler at me, send me an email, or talk to me in class. We'll make sure you got this. All right, hope you have a great day, and we will talk to you soon.